Hello my dear friends, welcome to CS with RS. Today we are going to discuss on a topic that's known as permutations. Now before I start, let me make an honest confession with you guys. When I was in school, I literally struggled with topics like permutation, combination and probability. Well, I'm not sure about you guys. Some of you might have been comfortable with these topics, while some of you might have been like me who have their own struggles with these topics. So, today, let's get comfortable with these uncomfortable topics. Let's understand permutations to its very core, to its very depth. And not just that, by the end of this session, you will not just develop the understanding of permutations, but you will also understand how these fundamental principles of permutations gets applied in real world machine learning problems. So let's start with the roadmap for this video. We will start with factorials. Then we will proceed to discuss the fundamental principles of counting. Then we'll see what exactly is permutation. Then we'll see how permutations is calculated under certain conditions. Then there is another scenario for permutations where the objects are not all distinct. There are some repetition in objects. Then we'll explore the 4 use cases of permutation in real world machine learning problems. Let's start with point number 1, which is factorials. Now, before we start discussing the concepts of permutations, factorials is a very important point that we need to understand, because permutations don't just start with arrangements, they actually start with choices. Now, what exactly are factorials? For example, say I write n factorial. Say factorials, I say n factorial. So what exactly does n factorial means? N factorial is basically a continuous product of all natural numbers starting from 1 till n. Okay, so it could be 1 into 2 into 3 into 4 dash 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 into n minus 2 into n minus 1 into n. This is what this is 1 n factorial actually means. Let's take some examples to understand. Let's say I have one object A. In how many ways can I arrange this object? Well, the answer is 1. There's only one way to arrange it. If I make it 2 objects, A and B, how can I arrange AB? Well, I can arrange it A first and B in the second place, or I can have B in the first place and A in the second place. So there are 2 ways to arrange them. Now let's say I have 3 objects A, B and C. Now how can I arrange these 3 objects? Like how many ways I can arrange these 3 objects? Let's say I keep A in the first place. So now I have 2 choices. I can either have A, B and C, or I can have A, C and B. Now I keep B fixed in the first place. So I can either have BAC or I can have BCA. Next, I keep C fixed in the first place. So I can either have CAB or CBA. So for 3 objects, I have 6 ways of arranging these 3 objects. So what exactly is this arrangement? Arrangement here is nothing but the number of choices that we have for each position. This arrangement is nothing but number of choices for each position taken one at a time. For example, when we have 3 objects, like this case here A, B and C, we have 3 positions. This is position 1, this is position 2 and this is position 3. Now we have three choices here. We can have either A, B or C. Now once we take any one of these objects in position 1 and we fix it, for position 2 we have only two choices left. For example, when we fixed A here, for position 2 we can have either B or C. Okay. Similarly, when we fixed B in the first place, for second place we could have either A or C. When we fixed C in the first place, in the second place we could have either A or B. Now when we selected position 1 and position 2, two of our objects are already fixed. Now for position 3 we are left with only one object. For example, when we fixed A and B here, we were left with C. When we fixed A and C in first second position, we were left with B. Similarly in these cases, the third position had only one choice. Here it was C, here it was A, here it was B, here it was A. So the total number of ways of arrangement is the multiplication of all these choices that we have, 3 into 2 into 1, which is basically 6. Now another question that could arise here is, why are we multiplying them? Why not add them? Why not subtract them? Or even why not divide them? Well, it turns out all these choices are basically independent of one another. Okay, for every choice that we have for position 1, there are two choices for position 2 and there are one choices for position 1 when both these positions are chosen. So these choices are independent. Now there is one more thing that will be very helpful to us. Like we know 3 factorial is 3 into 2 into 1. 2 factorial is 2 into 1. 1 factorial is 1. It's okay till here. But what about 0 factorial? We have seen that it's basically reduction. We are reducing one number at a time. 3, then 3 minus 1 is 2, 2 minus 1 is 1. But when we do 1 minus 1, we will get 0 factorial. So we should remember 0 factorial is a constant whose value is fixed, 1. The value of 0 factorial is 1 and we must always remember it. Now let's take some examples of factorials and try to solve them. Let's solve these two problems on factorials one by one. So we know that n factorial is a continuous multiplication of n natural numbers from 1 to n. So basically for 30 factorial, we can say we can go from 1 to 30 or from 30 to 1. We can minus it one number one at a time. So it's 31 minus 1 will be 29. When we minus 1 from 29, it will be 28. Similarly, 28 minus 1 will be 27, 26, 25, 24 till 4 into 3 into 2 into 1. So this is 30 factorial. Similarly, 28 factorial will be 28, minus 1 will be 27, minus 1 will be 26, then minus 1 25 till 4 into 3 into 2 into 1. Now one thing, if you notice, this is factorial of 28. 28 into 27 into 24 into 25 into 24 dash 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 minus 1 minus 1 minus 1 till we have 4 into 3 into 2 into 1. This is also present here. Okay, this is same. So 30 factorial can basically be written as 30 into 29 into 28 factorial. Okay, so when we have 30 factorial divided by 20 factorial, so it is 30 into 29 into 28 factorial. Okay, and this denomination is also 28 factorial. We can cancel both these, numerator and denominator. Why? Because both are same. So the final answer is 30 into 29. This becomes our final solution. Now let's check the next example. Let's clean it up. Okay, so we have 11 factorial minus 10 factorial into 9 factorial. So here again 11 factorial can be written as 11 into 10 into 9 into 8 into 7 into again 3 to 1. Okay? 10 factorial can be written as 10 into 9 into 8 into 7 into 6 into 5 into 4 into 3 to 1. 9 factorial can be written as 9 into 8 into 7 into 6 into 5 4 3 2 1. So if you see, this 9 into 8 into 7 into 6 till 3 to 1 is present here in 10 factorial. It is also present here in 11 factorial. So it will be correct to say 11 factorial is 11 into 10 into 9 factorial. 10 factorial is 10 into 9 factorial. So here it was 11 into 10 and this is 9 factorial. Similarly for 10 factorial, 10 into 9 factorial, and 9 factorial is as it is. So for 11 factorial minus 10 factorial, we can write 11 into 10 into 9 factorial minus 10 into 9 factorial. So if we take common 9 factorial out, it becomes 11 into 10 minus 10. 11 factorial, 10 factorial. When we divide by 9 factorial, because in our question we have denominator of 9 factorial. So this becomes the entire problem. So 9 factorial gets cancelled out. Finally denominator is 110 minus 10, which is 100. This is the solution for this problem. So this is equal to 100. Now let's take another example. We have 2n plus 1 factorial divided by n factorial, and we need to prove that this is equal to 2 to the power n multiplied by 1 into 3 into 5 till 2n minus 1 and 2n plus 1. So first 2n plus 1 factorial is basically 1 into 2 into 3 into 4 into dash 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 2n minus 1 2n and 2n plus 1. So this is basically 2n plus 1 factorial. Now we can do one thing here. We can separate the odd numbers and even numbers. We can do this. So it becomes 1 into 3 into 5 into 7 into dash dash 2n minus 1 and 2n plus 1. So this is set of odd numbers and they are multiplied by set of even numbers, 2 into 4 into 6 into till 2n. These are even numbers and these are odd numbers. So now even numbers, 2 is common here. Okay, so 2 is common. If we make it, for example, 2 can be written as 2 into 1, 4 can be written as 2 into 2, 6 can be written as 2 into 3, till 2n is 2 into n. So 2 is common here n times. So if we take this 2 common from here, this becomes 2 to the power n, 1 into 2 into 3 into 4 till n, and we know this is n factorial. So this becomes 2n into n factorial. Okay, so now when we substitute this even with 2 to the power n into n factorial, okay, this entire equation basically becomes this multiplied by 2 to the power n into n factorial. And here in our question we had this was completely divided by n factorial. So n factorial is common on both sides, it gets cancelled out. So it remains 2 to the power n, 1 into 3 into 5 into 7 into till 2n minus 1 into 2n plus 1, and this is what is required to be proven here. Now the trick that, or not just trick, the thought process that helped me to solve this problem is we separated odd numbers from even numbers. Okay, now let's move on to the next point. Another topic that we need to understand before we delve into permutations is basically fundamental principles of counting. Now, when we are counting the arrangement of objects, there are two approaches. We can either add those choices or we can multiply those choices. So we have fundamental principles of addition on one side and we have fundamental principles of multiplication on another side. Let's understand them one by one and also understand when to choose either addition or when we have to choose the principles of multiplication. We will understand that as well. So let's start with addition. Let's say we have to go to office. For example, we want to go to office. We have two options. Option number one is bus. There are three routes available. We can either choose route 1 or we can choose route 2 or we can choose route 3. So if we are going by bus, we have three choices available to us. Next, if we decide to go by metro, there are two routes. We can either choose M1 or we can choose M2. So we have two options available here. Now if you notice clearly, this selection is about or. We can go either by bus or by metro. Okay, pay close attention here. So this is either bus or metro. It's either or. So the number of possibilities of bus and the number of possibilities of metro are added. So they become our total possibilities. So we have three options to go with bus. At the same time, we have two options to go by metro. So together we have five options to choose from. Okay. So either if we go by bus, we have three options. If we go by metro, we have two options. So total we have five options to choose from. Similarly, in this second case, we have to select one snack. Now, that one snack could either be chips, okay, or it could be chocolate. Sorry, either a chip or a chocolate. Okay, so if we are selecting chips, we have four choices here. Okay, we have, let's say, CH1, CH2, CH3 and CH4. We have four chips. And for chocolates, we have C1, C2, C3, C4 and C5. We have five options for chocolates. So if we go by chips, we have four options. If we select chocolates, we have five options. So total options that we have are basically 9. Because here again, either chips, we can select either one snack amongst chips or one snack among chocolates. Okay, either a chip or a chocolate. So 4 plus 5, 9. We have overall 9 options here to choose from. We can choose one amongst them, and in this example we had 5 options to choose from. And one thing to remember here is all these options that we are talking about, these are distinct objects, distinct choices we can say, or distinct objects. So all these objects are basically mutually exclusive. Why? Because these choices are distinct. These are, another way of putting it, these are mutually exclusive choices. There are no resemblance between any one of them. All of them are distinct. Next is fundamental principles of multiplication. Now, addition was about either or, either option number 1 or option number 2. But for multiplication, multiplication happens when there is a sequence of choices. Let's say I made, for example here, I made choice 1, then I made choice 2, then I made choice 3, and let's say then I made choice 4. So choice 2 is dependent on choice 1, choice 3 is dependent on choice 2, choice 4 is dependent on choice 3. So let's say if the outcomes were x1, x2, x3 and x4. So all these choices are dependent upon one another. So final outcome is x1 into x2 into x3 into x4. So in multiplication case, we have a sequence of choices that are dependent on one another. First, then second depends on first, third on second, fourth on third, and so on. So this is where multiplication comes into the picture. Let's take two examples to better understand this. Suppose we are dressing up. Okay. Now when we dress up, we have an upper garment and we have a lower garment. So we wear shirts and pants. So shirt at the top and pant will be at bottom. So here both are happening together. It's not that we have to wear either a shirt or a pant. Okay, we cannot just dress up and say, okay, I've worn the shirt and I'm dressed up. No, where's the bottom? And we can't say we have put on the pants and we didn't put on shirt. So in this case, shirt and pant, both of them are needed. Okay, so for shirt and pants, we have three choices for shirts. Okay, we can either select shirt number 1, number 2, number 3. Similarly, we have two choices for pants. We can either have one pant or we can have two pants. So since choices are happening one after the other, okay, they are 3 into 2. So final outcome will be here 6. Similarly, if we take another example, let's say we have to create a password. Okay, and this password is basically 2 digits. Hypothetically, in a hypothetical scenario, we have to create a 2 digits password. And the options that we have here, we can have digits from 0 to 9. So these are basically 10 digits. Then we have special characters 1, 2, 3, 4 and 5. We have 5 special characters. So overall we have 10 plus 5 equal to 15 options to choose from. Okay, so a password has two fields. This is field 1, this is field 2. So we have 15 options here to choose from. And again, see the term when we are discussing, it came and. Once we select position number 1, we have to select position number 2. So how many choices we have? We have 15 choices here for position number 2. So it's basically 15 into 15. Total number of ways in which we can do that is 15 into 15, which is 225. So what differentiates between the whether we have to select fundamental principle of addition or we have to go with multiplication, which one to select? Do we need to add or do we need to multiply? We need to ask one question. Are these events which are happening or arrangements or choices here, whatever is happening, are these dependent on one another? Are these dependent on each other? This is the question we must ask. If the answer is no, then this is the case of addition. We need to add them. Why? Because this is a case of either or. either A can happen or B can happen. And if these choices are dependent on one another, then this is the case of multiplication. Choices are dependent. A1 into A2 into A3 into dash dash. So this is a case of multiplication. Here possibilities of A add with possibilities of B. And for example, if this was again case of 2, so we have number of choices for A multiplied by number of choices for B. Let's practice some problems on these fundamental principles of counting. We will explore cases for both addition and multiplication. The first problem is related to distribution of scholarship. We have 3 candidates for classical, 5 for mathematical and 4 for natural science scholarships. So we have 3 categories here. Classical is 3. For mathematical we have 5. And for science we have 4. Okay. 3, 5, 4. So the first question is, in how many ways can these scholarships be awarded? So if you notice carefully, it's saying in how many ways can these scholarships be awarded. So it's talking about all of these scholarships. Okay. All of these scholarships amongst all these 3 categories. Okay. So classical scholarships can be awarded in 3 ways. Mathematics can be awarded in 4 ways. Science can be awarded in, maths can be awarded in 5. Science in 4 ways. Now, let's understand one thing carefully. We need to distribute 3 scholarships from classical category, and we need to distribute 5 scholarships from mathematical category, and we need to distribute 4 scholarships from science category. So since it's talk about and means multiplications. 3 into 5, 15 into 4, 60. So total there are 60 ways of distributing all of these scholarships. Now the next question here is, in how many ways one of these scholarships could be awarded? One of these scholarships. Now one of these scholarship means we need to award only one scholarship. So it is the case of either the scholarship could be awarded from classical category, or from maths category, or from science category. So we have 3 categories. It's either classical or maths or science. So we are talking about or. Okay. This is or is case of addition. So classical there are 3 ways, maths there are 5 ways, science there are 4 ways. But we can choose either one of the category. So if we choose classical, there are 3 ways to award one scholarship. Or if we choose maths, there are 5 ways to choose one scholarship. Or if we choose third category, there are 4 ways to award one scholarship from science. So overall 5 plus 3, 8 plus 4, there are 12 ways to award one scholarship from all these 3 categories. Now moving on to next question. Next problem is, find the number of 4-letter words with or without meaning which can be formed out of letters of the word rose. So we have one word here, rose, which has 4 letters. Okay, 4 letters, that means they are distinct letters. Okay, R, O, S and E. Now it is saying we need to form 4-letter words. 2 conditions. First is repetition of letters is not allowed. Repetition is not allowed. So if we choose R, then in the next 3 places in a 4-letter word we cannot have R. Okay, every letter is unique here. Okay, so since there are 4 places, this is position 1, 2, 3 and 4. Okay, these are positions. Now when we have to choose a letter for position 1, we have 4 options. We can choose either R or O or S or E. So there are 4 choices. Now once we choose one letter amongst these four, we are left with now three choices. Let's say if we choose R for position 1 here, suppose it was R, then we have OSE. If we chose O, we are left with RSE. If we chose E, we are left with ROS. Similarly, if I chose S, I am left with ROE. Okay. So similarly, next when we came for second position, we had three options. When we finalize, we have three options. Now when we choose one, let's say I chose O. Now I'm left with two options for position number 3. If I was having this case, now when I chose R, I am left with S and E. For this case, when I choose E for first position, R for second position, I am left with O and S. Similarly, when I chose S for first place, R for second place, I am left with two more positions, O and E. So third position can be filled in two ways. Now once I select third position for all these four options, you can see I am left with only one letter to choose from. For first case, I have E, E, S and E. Okay, so I have only one way to choose the final letter. And again, we have 4, 3, 2, 1. As you can see, these depends are basically sequential. They are dependent on one another. Once I select for position 1, then I select for position 2, then for position 3, then for position 4. So there is a dependency of sequence. So it's multiplication. This is basically 4 factorial, which is 24. Okay, so filling position 1 another way, filling position 1 and filling for position 2 and filling for position 3, filling or choosing or selection, whatever we want to say, and we select for position number 4. So this is AND. So this is case of multiplication. Now the next question here is repetition of letters is allowed. Now the situation changes here. Okay, repetition is allowed. Okay, now for all these four positions, I can choose first position ROSE. There are four ways to choose this position. Since repetition is allowed, it doesn't matter which letter I have chosen for position 1. I again have choices 4 for position 2. Again, I can choose 4 letters amongst 4 letters for position 3. And again, I have 4 options for position number 4. Again, this is the case of AND. So for position 1, I have 4 options. For position 2, I have 4 options. Again, for position 3, 4 and position 4, 4. So multiply. So this is 4 to the power 4. So I have 4 to the power 4 ways, or 4 to the power 4 words I can form when the repetition of the letter is allowed. Let's take another question. Find the total number of ways of answering 5 objective type questions. Now here I have 5 objective type questions. Each question is having 4 choices. Let's say I have 5 questions. Question 1, question 2, question 3, question 4 and question number 5. So all these questions, this is having 4 choices, this is having 4, this is 4, this 4 and this 4. So if I have to answer question number 1, I can choose any one of the 4 choices. I have 4 options here. I can select one amongst the 4 options. Similarly, I can choose one amongst 4 for question 2. Similarly, I have 4 choices for 3, 4 and 5. And since these questions are not dependent upon one another, okay, I have to answer question 1 and I have to answer question 2 and I have to answer question number 3 and I have to answer question number 4 and I have to answer question number 5. So it means 4 into 4 into 4 into 4. So this is basically 4 to the power 5. So there are 4 to the power 5 ways of answering these 5 questions, having 4 choices each. Okay, 4 to the power 5. Let's take one more question. How many numbers are there between 100 and it should be 1000, in which all digits are distinct? So 100 to 1000, how many numbers are there in which all digits are distinct? So clearly we are talking about three-digit numbers here, position 1, 2 and 3. Okay, 3 positions here. Now first position can be filled from, when I'm talking about position 1, how many options do I have? I can select from 1 to 9. Of course I cannot select 0 in first position, that's not allowed. So I have 9 options to choose from for positions 1. Okay, now since we are talking about distinct numbers, the question mentions distinct numbers. Distinct means repetition of numbers is not allowed. All digits are distinct means repetition is not allowed. Okay, now once I have selected 1 amongst 1 to 9, how many options do I have for position number 2? So from 1 to 9 I am left with 8 options because I've chosen 1, but for position number 2 I can also select 0. Okay, so total it becomes, I have 9 options. From 1 to 9, since I chose 1, so I was left with 8 options, but for position number 2 I can select 0. So there are, this is 1 option, just not to confuse. Okay, 8 options plus 0 is 1 option. We have total 9 options. Okay, now out of okay, so basically 1 to 9 is 10 digits, and once we include 0 as well, we have 1 to 9 is 9 digits. Once we include 0, we have total of 10 digits. When I have to say 0 to 9 is basically 10 digits. So first position is filled, second position is filled, 2 positions are already filled. That means 2 letters are chosen from 10 digits. Now I am left with 8 digits. So position number 3 can be filled in 8 ways. And since these are sequential, position 1 and we have to fill position 2 and we have to fill position 3, so total number of ways are 9 into 9 into 8. So these many numbers exist which are having unique digits. Okay, there is no repetition of digits which is present here. So what exactly is permutation? So far we have seen several examples where we have performed arrangements of objects. So a permutation is basically arrangements of all these things which are either taken all of the things at a time or some of the things at a time. That's basically what a permutation is. And there are two things that happens in permutation. First, we select. Okay, for example, if we want to arrange 2 things out of 5, so we select these 2 things out of 5 and then we arrange. For example, let's say I have 5 letters. I am having 5 letters, but I want to arrange 2 letters. So first I will select. My first step will be to select 2 letters out of 5 which are given, and then next I will arrange them. I will arrange these two letters. So one very important thing that we must remember is permutation is basically selection first. First comes selection and then comes arrangement within that selection. This is one core concept that we must remember of permutation. And how we denote permutation is NPR, where N is total number of objects and R is the objects taken for arrangements. Objects taken at a time for arrangement. Okay, so NPR is basically denoted by n factorial divided by n minus r factorial. Now let's try to solve some problems on permutation. We'll start with first. In how many ways can 3 students be selected and arranged from 5? So here we have total students are 5 and we are asked to select 3. So n is 5, r is 3. So when we apply this formula, it becomes 5 factorial divided by 5 minus 3 factorial, which is 5 factorial divided by 2 factorial. 5 factorial is 120 divided by 2, which gives us 60. So there are 60 such ways to select and arrange 3 students out of 5. Now next is there are 7 athletes who are participating in a race. In how many ways can the first 3 prizes be won? Okay, so total athletes are 7 and prizes to be won are 3. So n is 7, r is 3. Okay, the question says out of 7 athletes, in how many ways can the first 3 prizes be won? First 3 prizes. It's talking about first 3. So it means athlete who comes at position 1, athlete who comes at position 2 and athlete who comes at position 3. Rest A4, A5, A6 and A7, there are no prize for them. So if we talk about the thought process, we are not mentioned here the specific athletes. These could be any 3. Okay, so first it's talking about selection of 3 athletes out of 7. Next, once we select these 3 athletes, now the prize could be given in this order A1, A2, A3, or the prize could be given in this order A1, A3, A2, or the prize order could be A2, A1, A3, or it could be A2, A3, A1. If we have A3 here, we can have A3, A1, A2 or A3, A2, A1. So there are multiple possibilities. So now next is arrangement of these 3 selected athletes. So one approach is to use the formula NPR. We can have 7 factorial upon 4 factorial, that will be the answer. So it will be 7 into 6 into 5, because after that there will be 4 factorial divided by 4 factorial, so they will cut off. So it's basically 7 into 30, which is 420. Okay, another way could be use our intuition. Again, next session that we are going to cover will be on combination. So just to give you a rough idea, like permutation is defined using NPR. Combination is about selection. Permutation is about selection and arrangement. But combination deals only with selection. And NCR is denoted by n factorial divided by r factorial into n minus r factorial. So when we have to select 3 athletes out of 7, so that could be done in n7C3 ways. And then we have to arrange these 3 athletes. So that arrangement can be done in 3 factorial ways. So once we solve it, 7 minus 3 will be 4. 4 factorial into 3 factorial. So they get cut off. So we are again here 7 factorial upon 4 factorial. That is same 420. So that is another approach. This is a formula based approach using NPR, and this is intuition based approach. Moving on to next question. It is required to seat 8 men and 4 women in a row. So we are provided information here is 8 men and 4 women are to be seated in a row so that the women occupy even places. Okay, so 8 plus 4 basically 12. So there are 12 seats. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If we number them, okay, these are seats. It is saying that women are to occupy even places. So 2, 4, 6, 8, 10, 12. There are 6 even places. Okay, so how many such arrangements are possible? Now there are 4 women and there are 6 even places. So women can be seated in these 6 places. So first we seat women, and then second we seat men. Okay, so for women there are 6 places and we have to, it's 6p4. Okay, we have to select 4 women amongst these, we have to select 4 places amongst these 6 and then arrange them. Okay, so 6 factorial upon 2 factorial. Even if we go by selection route, so we have to select 4 places out of 6, okay, for seating women, and then we can arrange 4 women in 4 factorial ways. So it will give us 2 factorial, 4 factorial into 4 factorial. So cross it off. So again we reach to 6 factorial divided by 2 factorial. Okay, now we talk about seating men. Now remaining, there were 6 odd places for men to be seated, and there are 2 places, 2 even places. Okay, because places were even, seats were 6 but women were 4. So now there are total of 8 seats for 8 men. So this could be done in 8p8 ways, which is 8 factorial by 0 factorial, and we know 0 factorial is 1, so this is basically 8 factorial. Okay, now the total number of such arrangements, we have to seat women and we have to seat men. So when end comes, it's multiplication. Okay, so women were seated in 6 factorial divided by 2 factorial ways, and men are to be seated in 8 factorial ways. So this is total number of such arrangements possible here. Moving on to the next question. We have 3 men have 4 coats, 5 waistcoats and 6 caps. Okay, so men are 3. We have coats, we have waistcoats and we have caps. 4, 5 and 3. 4 coats, 5 waistcoats and 3 caps. This is the information provided to us. The question is, in how many ways can they wear them? Okay. Now there are 3 men and they have to wear coat, waistcoat and caps. Okay. So again, it's talking about and one thing that we noticed from the question. Now, how can 3 men wear 4 coats? So first they have to select 3 out of 4 coats and then arrange them. Okay, like out of 4, if they have a C1, C2, C3 and C4 coats, even if they select C1, C2, C3, so men 1 could wear C1, men 2 could wear C2, men 3 can wear C3, or men 2 can wear C1, men 1 can wear C2 and men 3 can wear C3. There are multiple such arrangements which are possible. So this is 4P3 and waistcoat, so multiplication. How can 3 men wear 5 waistcoat? First select 3 waistcoat among 5 and then arrange it among themselves. And how can 3 men wear 3 caps? So first select 3 caps amongst 3 and then arrange them. So this is total number of ways. Let's take one more question. In an examination hall, there are 4 rows of chairs. Okay. So number of rows are 4. Okay. Each row has 8 chairs, one behind the another. Okay. So let's assume we have 4 rows: R1, R2, R3 and R4. 2, 3, 4, 5, 6, 7, 8. Similarly, we have 8 chairs here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So total there are 32 chairs. Now there are 2 classes sitting for the examination with 16 students in each class. Okay. There is class C1 having 16 students. There is class C2 which is also having 16 students. Now it is desired that in each row all students belong to the same class and no adjacent rows are allocated to the same class. Okay, so if we say we allocate row 1 to C1, then in all the 8 chairs only students of same class could sit. Either if C1 is allocated row 1, then students of class C1 could sit, or if C2 is allocated row 1, then students of class C2 could sit here. And another thing is, no adjacent rows are allocated to the same class. So if, for example, if C1 is sitting here, then C1 cannot sit here. Only C2 can sit here. If C2 is seated at R1, so C2 cannot sit at R2. It will be C1. So there are 2 possibilities. C1 is allocated R1, then automatically C2 is allocated R2. Since C2 is at R2, C1 comes in R3 and then C2 comes at R4. If R1 is allocated to class 2, then R2 is allocated to class 1, and then row 3 is allocated to class 2 and row 4 is allocated to class 1. So either approach, either selection or either approach would work. Okay, so what we need to do, we need to select permutation or arrangement for this, both of these possibilities here. Okay, so let's say R1 is allocated to C1. So there are 8 rows and 16 students. So when we go for first case, we need to select first of all 8 students out of 16 to seat at R1 and then arrange them. So it's 16P8. And we need to select remaining 8 students in R3. So and it's 8P8. Okay. This is for C1. Now similarly for C2, we need to select 8 students out of 16 to be seated at row 2, and remaining 8 students are to be seated in row 4, so it is 8p8. Now for second approach, we need to seat C2 class 2 at row 1. So again we need to select, we need to arrange, first select 8 students out of 16 and then arrange them in row 1. So 16p8, and then remaining 8 students are to be seated in row number 3. So it is 8p8. This is for class 2. Now for class 1, similarly, R2 is allocated to C1. So 16p8, 8 students to be selected from 16 and then arranged in row 2, and remaining 8 students are to be arranged in row number 4. So the total permutation will be addition of this and this, because it's the case of either approach 1 or approach 2. Let us now move on to the next point, where we are given certain conditions, and under those conditions we are supposed, or we are asked to find out the permutations. Let's take an example. How many 3-digit numbers can be formed using digits 1, 2 and 3, and repetition of these digits are allowed? So we are given digits here 1, 2, 3, and we are asked to find out how many 3-digit numbers could be formed. This is digit 1, digit 2 and digit 3. So repetition is allowed. Okay, repetition is allowed. So we have 3 choices here for digit 1. Since repetition is allowed, we again have 3 choices for D2, and for digit 3 also we have 3 choices. So overall we have 3 into 3 into 3 choices, which is 27. So we can say 27 3-digit numbers can be formed in this case. Next is permutations when a particular item must occur. Okay, how many arrangements of the letter Delhi are possible if D must be at the first position? Okay, so we have here Delhi. So it's saying that we have fixed D in the first position. So how many letters are, how many words are possible? D is fixed. Next we are left with 4 choices for ELHI. Okay, and here repetition is not mentioned. Okay, so this is a case where we have to select from out of these 4. Okay, so for this position 2, 3, 4, 5, D is fixed for position 1. For 2 we have 4 options. We can select either 3, E, L, H or I. Okay, now we are left with 3 options. Okay, let's say 1 amongst 4 is chosen, so now we are left with 3 options. So third position can be selected in 3 ways. Now since 2 are selected, we are left with 2 options. So 4th place can be filled in 2 ways, and last 5th place can be filled in 1 ways. So overall it's 4 into 3 into 2 into 1, which is 24. Twenty-four arrangements are possible. How many arrangements of word Ramesh is possible if R and A must always come together? R-A-M-E-S-H. If R and A must come together, R and A must come together. So let's consider R and A as one entity. This is one entity. So remaining 1, 2, 3, 4. So these 4 letters could be arranged in 4 factorial ways. Okay. Now amongst RA, it could be RA or AR. It is not saying that the order is fixed. It's saying that the R and A are together. So it can be together in 2 ways. So 4 factorial and into 2 are the total number of arrangements which are possible. Next is distinction between some items is ignored. So arrange A, B, C such that A, B are identical for counting purposes. So we have to arrange A, B and C such that A and B are identical for counting purpose. So first, the number of ways of arranging 3 things are 3 factorial. Now it's saying that A and B are identical. A and B are identical means when we say the total arrangement is 3 factorial, so these are counted as extras since these two are identical. So total number of arrangements will be 3 factorial divided by 2. Why we are dividing by 2? Because the condition is mentioned A and B are identical. So total number of arrangements is 3 factorial. So we divide by this case A and B are identical because we have counted them extra. Okay, this in total we consider them as non-identical, but since these are identical we divide by 2. Let's practice some problems on this permutation under certain conditions. In how many ways 5 boys and 3 girls be seated in a row so that no 2 girls sit together? Okay, so we have 5 boys and 3 girls are to be seated such that no 2 girls are together. So let's say we sit 5 boys. 5 boys can be seated in 5p5, that is 5 factorial ways. So I have boy, 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 boy and boy. When we sit 5 boys, 1, 2, 3, 4, 5 and 6 places comes up. Okay. Now the condition is no 2 girls can sit together. So we cannot have girl and girl. There must be a boy in between 2 girls. So when we have 5 boys seated, there are 6 positions available for girls to be distributed. So total positions for girls are 6, girls are 3. So out of 6 positions we need to make 3 girls sit there. So it's basically selecting 3 positions out of 6 and then arranging them. So it's basically 6p3. So total number of ways is 6p3 into 5 factorial. 5 factorial is how we can arrange boys. 6p3 is how we can arrange girls. And we multiplied why? Because this is the case of AND. Arrange boys and arrange girls. Next question is, in how many ways can the letters of the word pencil be arranged? Okay, we have a word here, pencil. How many ways can the letters of this word be arranged so that N is always next to E? Okay, so it is saying that first condition, N is always next to E. So E, N are basically together as 1. So P, E, N, C, E, L. Together there are 6 letters here. But when we consider E and N together, now total letters are 5 for this condition. Okay. So how we can arrange 5 letters is through 5 factorial. This is the answer. Second, n and e are always together. Now, in this case, it is saying that e and n are together. So here also E and N are considered as one letter. So we are left with 1, 2, 3, 4 and 5. So 5 factorial. But one thing to notice here, in previous case it said that N is always next to E. So E was in En, E was in first position, N was in second position, and this was fixed. But in second case it is saying that N and E are always together. It's not talking about the order. It could be NE or it could be EN. So the total number of ways of arranging is 5 factorial into 2. 2 for this arrangement, NE or EN. Next is how many different words can be formed with letters of the word equation, so that we have equation, the words begin with E. Okay, so it's saying that E is fixed. 1, 2, 3, 4, 5, 6, 7 and 8. There are 8 letters. So when we fixed E, we are left with 7 letters. So how many letters, how many words can be formed is basically the arrangement of 7 letters used together. So 7 factorial words can be formed when E is fixed in first position. Next is the words begin with E and end with N. The words begin with E and end with N. So what it is saying as E is fixed, N is fixed. There are 8 letters, 1, 2, 3, 4, 5, 6, 7 and 8. So 1 and 8 are fixed. We are left with this 6. We are left with this 6 positions. So how many letters, how many words can be formed is basically the arrangement of these 6 letters. The words begin and end with a consonant. Now in equation, two, 3. There are 3 consonants and 1, 2, 3, 4, 5. 5 vowels. So it is saying that the 2, 3, 4, 5, 6, 7, 8. 8, 7, 6, 5, 3, 2, 1. The first and the 8th position is occupied by consonant. The words begin and end with a consonant. So there are 3 consonants and there are 2 places, okay, to place these consonants. So how many ways can it be done? Out of 3, we need to select 2 consonants and then arrange them. So it's basically 3p2. Okay, and then we are left with these 6 positions. So 6 letters can be arranged in 6 factorial ways. So the final answer is 3p2 into 6 factorial. Let us now move on to the next topic, where we find out permutations in a condition where not all objects are same. Let us move on to the next topic, where we find out permutations given condition that not all objects are distinct. There are some repetition in the objects which are provided to us. So in this case, let's say there are total elements are n. So we know that the permutation is n factorial. But we say the repeated elements, let's say there is one For example, we take an example of letters. Okay, we have a word made up of n letters. Okay, so the total number of ways of arranging them is n factorial. There is one letter A which has repetition in p1 times. Now we have another letter, let's say B, which has repetition in p2 times. Similarly, we have a third letter which is C, which has number of repetitions as p3. So the final probability will be n factorial, which is the total number of letters, divided by p1 factorial into p2 factorial and p3 factorial. Okay, so suppose there are 10 letters in a word. Okay, and letter A is repeated 2 times, so p1 is 2. Okay, letter B is repeated 3 times, p2 is 3, and C is repeated 2 times, so p3 is 2. So total permutation will be 10 factorial, n is 10, divided by 2 factorial into 3 factorial into 2 factorial. And why we are dividing? This is one very important question here, because when we say 10 factorial arrangement, okay, if all the letters are distinct, then it is fine. Okay, 10 factorial assumes that all the 10 letters in the word are distinct, but that's not the case. When we have repeated element, for example, I say AA, okay, on paper these are looking same, whether I say AA or whether I swap their places. Okay, final outcome will again be AA. So there is no difference between this AA and this AA. Okay, so this is overcounting. So to reduce that overcounting in our calculation, we divide. Okay, this is the case of overcounting. So to remove that overcounting in our calculation of 10 factorial, we divide by the number of the factorial of the number of occurrences or the repetition. Similarly, when we say B, 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 now how many ways to arrange these 3 letters is 3 factorial. Okay, but if even I swap these places, final outcome will be B, B, B. This is 6. Okay, so I say B, B, B one more time, 2 more times. So the number of ways to arrange 3 letters is 3 factorial, which is 6. So this is 1, 2, 3, 4, this is 5, this is 6. So out of these 6 arrangements, do you see any difference? Well, the answer is no, because each of these arrangement is same. So this is over calculation here. So that's the reason we divide the total number of ways by the repetition. Okay, that's the reason, because this doesn't count. Let's look at some more examples. How many permutations of the word apple is possible? Okay, we have apple A, P, P, L and E. So how many permutations are possible? 1, 2, 3, 4, 5. So n is 5. It's 5p5, which is basically 5 factorial, but p are 2 here. So pp, even if we swap place, it will be pp. So no difference. So this is extra calculation. So we divide by 2 factorial. This is the final answer, which is 120 upon 2, which is 60. Next is how many permutations of Mississippi? Similarly, M, I, S, S, I, S, S, I. PPI. So we have I is 1 4 times, S is 4 times, P is coming 2 times, S is 4 times, P is coming 2 times. M is coming one time. 1 2 3 4 5 6 7 8 9 10 11. There are total 11 letters. So the total permutation will be 11 factorial divided by repetition, which is 4 factorial into 4 factorial into 2 factorial. Okay, 11 are letters. So if 11 letters were all distinct, total permutation will be 11 factorial, but that's not the case. We have I, which is occurring 4 times. So we divide by 4 factorial, because again 4 factorial is 24. Even if we make 24 such arrangements, they all will be identical. That's why they are over calculated here in 11 factorial. So that's the reason we divide. Okay. How many permutations of A, B, 3 letters, so 3 factorial, but A are occurring twice, so divide by 2 factorial. Similarly, how many distinct numbers can be formed using digits 1, 1, 2, 2? So these are 4 digits. So unique combination will be 4 factorial, but 1 is occurring 2 times. Similarly, 2 is occurring 2 times. So this is the answer. 24 by 4, which is 6 unique numbers can be formed. Okay, let's practice some more problems. How many different words can be formed with letters of the word Mississippi? Okay, we just saw Mississippi. These are 11 letters. Okay, S is occurring 4 times, I is occurring 4 times, P is occurring 2 times, and M is occurring 1 times. It is saying the condition how many of these permutations have 4 I's do not come together. So we saw total is 11 factorial divided by 4 factorial into 4 factorial into 2 factorial. Now it is saying in how many of these permutations 4 I's do not come together. Okay, so 4 I's do not come together. So now one way to find out is, we know this is the total number of letters that could be formed. Okay, now we can figure out a case where 4 I's are coming together. This is one common approach to find out the cases where things don't happen. Okay, find out the total number of ways minus the possible ways of given condition. That gives us the cases where things don't happen. Okay, total minus things that could happen will give us things that could not happen. Okay, for example, if there are total 10 ways for something to happen, okay, and we say there is given condition, and the total number of ways that condition could happen is 4. So the total number of ways when that condition could not happen will be 10 minus 4, which will be 6. Okay, so when 4 I's are together, it will form one letter. Okay, so now there will be S will be 4, I is 1, P is 2, M is 1. So total is 4, 5, 6, 7 and 8. So 8 factorial divided by 4 factorial into 2 factorial. So the total number of ways in which 4 I's are not together is this. We take this total and we minus this from that. It will be 11 factorial divided by 4 factorial into 4 factorial into 2 factorial minus 8 factorial upon 4 factorial into 2 factorial. So these are the cases when 4 i's do not come together, and this is what we were asked to find out. Okay, coming to next question. In how many ways can the letters of the word permutations be arranged? Okay, we have permutations. Okay, 1 2 3 4 5 6 7 8 9 10 11 12. 4 letters, and do we have any repetition? Yes, there are 2 T's and then 10 distinct letters. Okay, so in how many ways can letters of the word permutations be arranged if the word starts with P and ends with S? So first position is P, last one is S. This is first, this is 12. Rest we have 2 3 4 5 6 7 8 9 10. From 2 3 4 to 9 10 and 11. So these are 10 places. Okay, P and S are together. So now we are left with 10 letters here. And amongst these 10 letters we have 2 T's. Okay, so the total number of ways will be 10 factorial divided by 2 factorial. Why? Because permutation is having 12 letters. When we fix P and S, we are left with 10 letters out of 12. 2 are fixed. So the number of ways of arranging 10 letters is 10 factorial. But amongst these 10 letters, we have 2 T's. Okay, so we divide it by 2 factorial. Next is vowels are all together. Okay, now vowels are, we have E, U, A, I and O. There are 5 vowels and there are 7 consonants. Okay, 1 2 3 4 5. There are 5 vowels. So it is saying that if vowels are all together, that means these 5 vowels, they form one letter. So now we are left to, we have total 7 plus 1, which will be 8 letters. Okay, so the total number of ways will be 8 factorial divided by 2 factorial. And these 5 vowels, since all of them are unique, could be arranged amongst themselves in 5 factorial ways. So 8 factorial divided by 2 factorial into 5 factorial. That will be the total number of letters when vowels are together. Let's take one more example. Let's take one more question. We have 6 periods in each working day of a school. Okay, the total number of periods are 6, and it is saying that in how many ways one can arrange 5 subjects. There are 5 subjects. Condition is such that each subject is allowed at least 1 period. Okay, say we have P1, P2, P3, P4, P5 and P6. 6 periods in S1, S2, S3, S4 and S5 as 5 subjects. So it is saying that each subject is allocated at least 1 period. So if one subject is allocated 1 period, then 5 periods are already occupied. We have 1 extra period. Okay, so first of all, there are 2 things here. One is subject to period mapping. Second thing is selecting a subject for the extra period. Okay, so we have 5 periods, we have 5 subjects. we can arrange them in 5p5 ways. Okay, and for the sixth period there are 5 subjects to choose from. Okay, we can select any one of the 5 periods, 5 subjects, sorry, we can select any one of these 5 subjects to fill this extra period, and remaining 5 periods can be distributed among 5 subjects in 5p5 ways. Now we can select one subject out of 5 subjects to fill the extra period which is remaining in 5c1 ways. Okay, and now we have 5 unique subjects and this one extra subject s of x, which will occupy this sixth period. So 6 periods can be arranged in 6 subjects can be arranged for 6 periods in 6 factorial ways, but out of these 6 subjects there will be 2 subjects which are repeating, so we divided by 2 factorial. So this is the total number of ways in which 5 subjects can be allocated to 6 periods such that each subject is having at least 1 period. Okay, let's revisit it. 5 subjects are unique. We select one subject out of 5 to fill for this extra period. Now when this happens, one subject s of x, we call it here, is repeated amongst these 5. It could be s of 1, s of 2, 3, 4 or s of 5. So the total number of ways to arrange 6 subjects in 6 periods is 6 factorial. Okay, but we have one subject which is repeating, occurring twice, so we divided by 2 factorial. So these are the total number of ways. Next, let us look at some of the practical use cases where permutation is useful in machine learning. Let's start with first, which is permutation feature importance. Interpretability. Interpretability is basically a term where we humans try to understand the internal working of a model, you could say, or it's like which inputs are basically responsible for the output which is generated by the model, and to what extent are these inputs responsible for that specific output. So this learning that we humans do under this the working of the machine, that's basically roughly is what this term interpretability means. So let's take one example of credit score to understand which feature basically holds the importance, okay, which has higher importance, we can say that, for the specific output which is being generated by the model, and we permute these features to understand. Okay, the core concept here is we take a feature, we rearrange its values, and we see how the model is responding to the actual value. If the prediction falls so much, we can say that this specific feature basically holds higher significance or higher importance for this model. Okay, let's check out with an example. Okay, so we have a credit score feature here. Okay, we have customers A, B, C and D. We have 4 customers. We have the credit score 800, 650, 720, 600. We have their respective ages and the final default state. We know that customer A has default of no, customer B can default, customer C cannot default, and customer D can default. Now Now this model basically calculates this default on the basis of credit score and age. Okay, now this table that we have here, this prediction, this default is actually the actual prediction. This is actual prediction by model. Okay, and this is done using a combination of credit score and age. Lower credit score means higher chances of default. If we can see here, 650 and 600, these are low scores. This is low score, this is low score, and yes, the chances of default are yes. 800, 720 are higher scores, so the chances of default are no here. Age matters less, so the age of a person matters less here. Even if this person is 45 years of age, it might be 55, but still the default state will be no. Why? Because the weightage here, the model gives more weightage to the credit score. And finally, the model's accuracy is 90%. Now let's say we now want to find out which feature amongst credit score or age actually has higher importance in this prediction. Okay, so how can we do that? We'll use permutation here. Let's take one by one. Let's take an example of credit score. We rearrange these credit scores. Okay, so previously, if you notice, A was assigned a score of 800, C was assigned a score of 720. So those customers whose score was high initially are now being assigned low score. Okay, A and C. And on the other hand, B and D were having lower credit score. So now they are assigned a higher credit score here. B and D are assigned a higher credit score here. Okay, so now what happens? If you see, higher credit score is having default yes, higher credit score is having default yes. So high score people, customers with high score are now risky people marked in the prediction, and people with lower score are marked as safe people. So the accuracy has now reduced down to 55%, and this is a performance drop of 35%. So when we rearrange the credit score, this feature gets rearranged, the performance drops, and not just marginally, it drops significantly, 35%. Now on the other hand, let's try to rearrange the age. Okay, A is 45, now we make it 25. B is now made as 45 from 30. Similarly, C and D from 40 to 25, they are changed to 30 and 40. Now the default state is as it is. If we can see, age does not have much impact here on the default state. Just assume we have some logic and this new accuracy comes as 85%. There is just 5% drop in the performance which is being calculated by model, because as mentioned initially, the model's default status, actually credit score has a higher impact on the default state. Age does not have much of an impact. This is something that we knew about this model. This feature we knew initially. So when we rearranged credit score, it impacted the performance. But when we rearranged age, it does not have a maximum impact. 5% is a pretty lower impact. And why do we call it permutation? Now, where does permutation comes into the picture here? Because we have rearranged the values of features, and permutation is about selection and arrangement. So we selected one feature and we rearranged its values. We tried with credit score and age, but we found out that credit score impacts the overall performance more as compared to age. So credit score is a feature that matters more to this model. Another example where permutation is used in machine learning is in data augmentation. Now, data augmentation is basically a process where we use the existing data which is available with us to generate a newer data set from this existing data set. But such a data set should have meaning. It's not that since we are going to create newer data set, we create any meaningless data set. That's not the case. So let's use an example to check how this happens. Let's say I have a sentiment analysis system, okay, and let's say I have a sentence here: I really love this movie. Now this gives it a positive sentiment, okay, but the thing is my model has only this sentence. I am having only one sentence. Now the more data we have, the more we can say the better the prediction of the model is, okay. So just one sentence is not enough. So what do? We used permutation to create augmentation, okay. So we create same meaning different order. What it means is we rearrange the words present in this sentence, okay. This permutation basically means, you can say here, rearranging words. But one thing to notice is we cannot just randomly rearrange these words. We have to ensure that the grammar is considered, because we need to have a meaningful data, okay. So I create another sentence: I love this movie really. So this is also grammatically correct. Really, I love this movie. I love really this movie, okay. So to a good extent these are grammatically correct. Now might not be 100%, but at least 90-95% they make sense, okay. These are not just randomly jumbled words. So now my model, initially it had only one sentence, now it has three more sentences. So overall my model is having four sentences to get trained or for prediction. So now the prediction of my model is more optimized. Now what is the result of this? The model basically understand one thing, that when we have words like love, really and movie, okay, when we train model with this synthetic or user generated data set, the model understands that when we have these words coming together in a sentence, it means there is a positive sentiment, okay. So love, really, movie, now they can be in any order. Like we see here, I really love movie, love movie really, love really movie. So these are rearranged, these words are rearranged, but whenever they are appearing together in a sentence, it means it's a positive sentiment being expressed by that sentence. So this is another application of permutation. Why? Because we are rearranging the words in a sentence. Rearranging words, that's what we are doing to create new data set, okay. So that's another application of permutation. Now let's see a third application of permutation in machine learning, which is reinforcement learning. Let's now talk about action sequence optimization. So action sequence optimization is basically when an ML model basically performs an actions in multiple steps. So what it does, it rearranges the steps, and let's say there is some reward which is being provided for taking any action, and on the basis of that it calculates the total rewards that it has earned, and the sequence of actions which gets the maximum number of rewards is then finally chosen. So that's the idea behind this action sequence optimization. Let's better understand with an example. Let's say I am having the key point here, first of all, is same actions, different order and different outcomes. So we have same actions. Let's say we have A, B, C and D, 4 actions. Now we can do it in A, B, C, D way. We can create another arrangement A, C, B, D. We can even have B, C, D, A. So there are multiple such orders of same action, same 4 actions that we can perform, and on the basis of that each ordering will give us a different outcome. Okay, so that's basically the key idea behind this action sequence optimization. Let's take an example of an autonomous car which is approaching a slow vehicle. So let's say this is our car, it's moving ahead. Let's say it's driving with a speed of 90 kilometer per hour. Okay, and we have another car here, this is C1, this is C2, and somehow it is driving at just 30 kilometer per hour of speed. Now obviously this is at 90, this is at 30. If it does not do anything, it will hit this car from behind. Okay, so now what will the agent within this car will do? Okay, let's say if the current state for this car is okay, for an example, let's say this was a 60 kilometer, not 90. Let's say this is moving at 60 kilometer per hour. The distance between these two cars is 25 kilometers, and so example, say this is the road, it's a 2-lane road. Our car is here, this is C2. Okay, this is lane 1 and this is lane 2. So it has lane 2 is available. Okay, there is no car here as of now. So lane 2 is available for C2. Okay, and this distance is 25 meters. Okay, now what are the possible actions that C1 can take? Number one, it can increase the speed, it can apply the brake, and it will change the lane. Now for a moment, let's forget about the autonomous car, let's forget about machine learning. Let's say we are driving, we are in this C1 car moving at 60 kilometer per hour. We see another car which is slow, let's say 20 or 30 kilometer per hour speed, distance is 25 meters. What are we going to do? Obviously the first choice, if we are very close, then apply brake. Otherwise, if we have 25 meter is a decent amount of distance, we don't have to do braking, we can ideally change the lane. So obviously this is what we are going to do. If there is a requirement of brake, apply brake, slow ourselves down, maybe from 62 come to 40, change lane and then speed up. So that's ideally what we are going to do. Okay, so let's see how the agent will take actions here. Now there are 3 possible sequence of actions. Okay, first of all, the agent can first change lane, increase the speed and maintain this state. Second possible sequence that the agent can decide from is first speed up, okay, then change lane, then maintain the state. Third order here is apply the brakes, change lane and then speed up. Now which sequence should the agent decide? So here comes the award situation. Let's say situation first of all is the outcome for any action. Okay, if we are changing lane, then that's the new situation. If we are applying brakes, then it's a new situation. If we are speeding up, that's a new situation. So the outcome of every action is being assigned some award here. Okay, so let's say this self-driving state is 10, reach target speed is 5, we have near collision state is minus 20. So these are positive outcomes. That's why they are being assigned positive numbers. It should not be self-driving, it should be safe driving. Okay, safe driving state. If there is near collision, it is minus 20. If collision is happening, then we abort it with minus 100, because ultimately two cars have collided. For unnecessary braking, we go with minus 2. Now for every sequence, if you see here, change lane is assigned 10 marks. Let's start with sequence number 1. We have 10 for change lane, speed up gets plus 5. So total it's, and the state is maintained. So now no award for this. So total is plus 15. Now coming to second sequence, speed up, but this speed up is assigned minus 20. Why? Because it increases the risk. Now this is a near collision state, that's why it is being assigned minus 20. Okay, because in this first example, when we changed lane, nothing is there in front of us, we can easily speed it up, so it was a correct choice. But in second case, if we speed up, we are very close to a collision, that's why it's assigned minus 20. Then changing lane is a good choice, correct choice, but the final result is minus 15. Third, we apply brake, we slow ourselves down, so it's assigned minus 2. Then we change lane, which is assigned plus 10. Then we increase our speed. Now this action is allocated 5 points. So overall it's plus 13. Okay, so which sequence of actions can this agent choose? Obviously it's first one, plus 15. Just change the lane, increase your speed, and then maintain the state. That's what we as humans, if we were driving, we would have chosen this first sequence. Okay, and how is permutation involved in all of this? Same actions, change lane, speed up, or braking. Okay, but their ordering is different, their arrangements is different. So this is another application of permutation in case of self-driving cars. Okay, let's check out one more example before we end this session, and that is hyperparameter tuning and optimization. First, let's understand the difference between parameters and hyperparameters. Parameters are something that are learned from the data, like for example, what's the slope, what is the gradient that we discussed earlier. So things like these are basically learned from the data itself. Okay, the model does that, but hyperparameters are something which are decided by us engineers before the model starts processing the data. These are decided by us, and a model does not know by itself what are these hyperparameters. And now which hyperparameters to use, that's a question. Like for example, if we have multiple hyperparameters like learning rate or number of trees or batch size, so we can, this is where permutation and combination comes into the picture. Like permutation is about selecting and arranging, so we can select n number of these hyperparameters, and we can see how does this optimization, model optimization results in. Let's better understand with a small example. Okay, I know it's a pretty an advanced topic in ML, and to be honest, even I'm not 100% sure about this topic, but I took it up just to have a glimpse of it, and in our later sessions we will definitely explore the concept of hyperparameters in depth. Okay, so let's say there is some random forest training, we take this example, and what we do here, we have three parameters, hyperparameters. We have number of trees. Let's say we take two items here, two values, 50 and 100. We have max depth, where we have again two values, 3 and 5. We have a learning rate with two values, 0.01 and 0.1. Now we have three parameters here, hyperparameters. So how many combination can we make? We can make 8 combinations here, because each of the parameters is having two values. So overall we can make 2 power 3, 8 choices here. Let's say for example, this we have some configurations, like we select 50 from number of trees, we have 3 as max tab, 0.01 is the learning rate, and let's say the accuracy that we get from the model using these hyperparameters is 83%, and similarly we do it for the other set of hyperparameters, and then finally we see that okay, this 91%, this basically is coming from this set of parameters, which is 100, 5 and 0.1. okay, this one. So this set of hyperparameters are basically selected, and it helps us in our prediction. It improves the accuracy of the model. And now, to be very honest, like it's, as I said, it's a very advanced topic, We will definitely explore it in depth. But just for now, just to highlight the importance of permutation, I just took up this example. Okay, here again the permutation comes into the picture. We are making selections. We are selecting from the hyperparameters which is available to us, and then we are arranging them, and then we are using this selection and arrangement to and apply to our model to find out the accuracy in percentage, and then we select one which we find to be the good option, and then we go ahead with this set of hyperparameters. That okay, this is what we are going to use in our model. Okay, so this brings us to the end of this session. Let us quickly revisit what we have learned in this session. We started with factorials, where we understood the possibilities of counting. Then we understood the fundamental principles of counting, where we understood where to apply addition, where to apply multiplication. Then we moved to permutation, where first we understood the basic concepts of permutations. Then we saw how permutation is applied under certain conditions. Then we also checked out some practical use cases where the concepts of permutations are actually applied in real world machine learning. As engineers, we must remember that in machine learning, we are not just arranging data or letters or numbers on papers. We are rearranging data, we are rearranging actions, we are rearranging parameters like hyperparameters in our last use case of permutations in machine learning. But at the core of everything what we are doing, whether we are rearranging like for sound waves, we saw one application of permutation in machine learning using sine waves for sounds and signals. So at the core of everything, okay, what we are doing, it's permutations. So if you like this video, please click on the like button and subscribe to the channel for future such videos, and see you guys in the next video. Till then, tata, bye bye.